Hello, welcome to another module of this course, Analog Circuits. So, in this module we shall be introducing you to a class of circuits known as current mirrors, which are also DC circuits based on the BJT devices, and they serve a very important purpose in providing the required bias currents various circuits. But before we go to the current mirror, let me also introduce you to the various small signal BJT models that are used. So, there are a number of models for BJTs reported in literature, of which two are very popular. The first one is known as the hybrid pi model. Okay. So, in this module, let us see first consider a BJT which is connected with proper bias voltages and currents. Now, note in this circuit I am not adding any DC sources, I have not added any DC sources like the VCC or VBB that I mentioned in the previous module. Instead, all the sources here are AC, okay, or the actual signal that has to be processed by the BJT. Okay. So, the equivalent circuit or equivalent hybrid pi circuit or hybrid pi model for this BJT is given like this. This is the hybrid pi model. First thing to note about this model is that this is a linear model. Even though the BJT is a fundamentally non-linear device, that is, the voltages and currents do not exactly have a linear relationship, this particular model linearizes the circuit over its active region. So, this particular model is applicable only in the active region, not in the saturation or in the cutoff region. Okay. The active region, by the way, is also known as the linear region of the BJT, because in this region the voltage and currents are somewhat linearly related, not strictly, but somewhat. So, once we linearize our BJT, then the model we get is something like this. Now, the important thing is, what are these parameters? To understand what are these parameters, let us consider the currents and voltages as represented by this model. So, I have my emitter current I e. So, this is my hybrid pi model, the current I e. Note that this I e is the AC current, okay, not the DC bias currents. This is the actual signal current that is present. And note also that this hybrid pi model or any other AC model of a BJT will always exclude the DC sources, because since we have linearized our circuit, we assume that the DC circuit, the final response of this circuit will be a combination of the DC and AC outputs, or the DC or AC currents and voltages at the various nodes. Hence, because of the linearity property of this BJT at its active region, we can separate the AC circuit out and just analyze the AC solution of this circuit. Later on, we can combine this solution with the DC solution, and the final output will be the sum of the two, or the superposition of the two. So, I e, my emitter current, is equal to, as I can see, of the collector current and the base current. So, this is equal to I b plus I c. Also note that I am using these small letters. The small letters, that is small I b or small v, they represent the AC signal, whereas capital V or capital I, they represent DC signals. So, what is my I b? I can see that I b is nothing but V b e upon R pi, okay, and I c is equal to G m times V b e. Okay. Here we are for some time ignoring this resistance R 0. Okay. If we ignore this resistance R 0, assume that the R 0 is infinite and no current is flowing through that, then this equation will be true. So, I can take V b e upon R pi common, okay, and that will give me 1 plus G m R pi. Okay. Here this pi should have been here, like this, and this I can say is equal to I b, because V b e upon R pi is equal to I b, and suppose I write it like this, then I get back my original relationship between I e and I b. I e and I b are related by this equation. Therefore, the beta of this small signal model is given by G m R pi. So, this is the equation relating the traditional beta. This beta is irrespective of whether you linearize the circuit or you have an equivalent model, beta is always present, but this G m and R pi are specific to this model, and this is the equation that relate the two. Okay. I can further proceed along the similar lines by considering the equation for I c. I c should be equal to I s times e raised to V b e upon V t. Here my V is the AC voltage, I c is the AC voltage. If I differentiate this with respect to V b e, then that will give us the value of G m, because after all G m is the dynamic transconductance, that is G m is equal to the change in I c due to a change in V b e. G m is not equal to simply I c upon V b e. This is the DC transconductance, but the AC transconductance is the, or the dynamic transconductance is the change in I c due to a change in V b e. So, once I get this value of G m, what is, if I now evaluate this derivative, then that comes out to be equal to I s e raised to v b e upon v t, this whole upon v t, okay. And this is again equal to I c upon v t. Okay. So, then G m is equal to I c upon v t. This is the formula. So, these were my two unknowns or for this model. One was this r pi and the other was G m. I found out G m was given by I c upon v t and r pi was given by beta upon G m from this equation. So, first I can find out G m from this equation, substitute it here, and I can find out r pi. So, this is how this model is defined. Now, another module that is very commonly used for the active region of a BJT is the T model. So, let us see what is the T model. Now, the R 0 that I had mentioned in the previous hybrid pi model will be defined by this, this when we discuss this particular model. So, here we see that this I b base current is equal to the difference between the collector and the emitter current, or I should say this is equal to I e minus I c, okay. And I e is given by V b e. So, this is my base upon R e, and I e is given by G m times V b e. So, this whole comes out to be equal to V b e upon R e multiplied by 1 minus G m R e, and this is equal to of the form I e multiplied by 1 minus alpha, which can be simplified to I e upon 1 minus beta upon 1 plus beta, which is equal to I e upon 1 plus beta, and which is equal to V b e upon 1 plus beta R e. Okay. So, here this alpha, my traditional BJT alpha is equal to G m R e, which implies R e is equal to alpha upon G m. So, this is how this R e resistance is defined. Okay. Now, comparing the values of R e and R pi that I had defined in the for the previous model, we can obtain a relation which I leave for you as an assignment to find out, that R pi will be equal to R e times 1 plus beta. Now, once these models are known, we can use these models for various AC, finding out the AC response of various circuits. For example, the common emitter circuit that we had discussed earlier, we can find its equivalent model either in terms of this T model or the hybrid pi model here. Connect the AC source that is being applied to the base of the original circuit and find out the voltage and current at the base and collector junction. So, that is how we solve for the AC response of a BJT. Since time is short and we do not have many modules left, so I will not be covering any further topics on the AC response of BJTs, but as promised at the beginning of this module, I shall be showing you a circuit which is known as a current mirror. Now, current mirror is a circuit that replicates a current. So, it is a mirror. The word mirror is used because the same current that is applied at one terminal appears across another terminal, and it is very commonly used in various circuits. For example, if we want identical operation of two amplifiers, then we cannot just simply design the circuit to ensure that the equal currents flow through them. We need to actually ensure it using current mirrors. So, we connect two branches of the current mirror to the two amplifiers, and since they are in mirror, there is a mirroring effect. So, the currents will definitely be the same in both the amplifiers. So, let us see how this current mirror is constructed. The circuit for this mirror is given like this. Now, at the beginning of this, at the beginning when we were first started discussing BJTs, I had mentioned that the current IC is a function of only VBE. This is true to some extent, but actually in reality IC is also a function of VCE. However, this dependence is very tenuous, not VCE does not influence, or variation in VCE does not change IC to that extent to which IC is changed due to changes in VBE, and we shall be assuming that IC or any of the other currents of a BJT are only functions of VBE. If that is the case, then from the way these two NPN transistors, these two NPN BJTs have been connected, we can see that the VBE voltage will be same for both. So, VBE1, suppose I call this transistor 1, this as transistor 2, VBE1 will be equal to VBE2. Hence, we can say that all the currents flowing through all the transistors, the respective currents in the various terminals of both the transistors will be the same. So, that is why we have the same current IB flowing through the base of both the transistors. Of course, these two transistors are themselves identical, okay, and so will be the emitter currents and also the collector currents. So, we can then write this current I ref as equal to IC plus IX, and Ix, as we can see, is equal to twice of IB, where IB is the base current flowing through the base of both the transistors. So I can write this as equal to IC plus 2 IB. Okay. Now IC should be equal to the collector current of this transistor, which in turn is equal to I0. So I can replace IC with I0 like this. IB in turn is a function of IC and given by IB is equal to I0 upon beta. Now this implies Iref is equal to I0 plus twice of I0 upon beta, which is equal to I0 into 1 plus 2 upon beta. So this implies that I0 upon Iref is equal to 1 upon 1 plus 2 upon beta. As we can see, I0 and Iref are not totally same. If beta is quite high, of course, then I0 will be equal to Iref. But if beta is till the time beta is not very high, there will be a small difference between I0 and Iref, and that is one problem with this kind of current mirror. True that Iref and I0 match each other very closely, since beta is usually quite high, but we have some other designs where this closeness of Iref and I0 is even more. So in this module we covered some topics on transistor modeling. We discussed about the two common AC models used in the active region of the BJT, that is the hybrid pi model and the T model, and we also discussed a simple current mirror using a BJT. Now this is the last module of this course that I shall be taking. After this module, the TAs for this course will be taking some tutorial classes. So those will be the subsequent modules of this course. It was really an enjoyable experience discussing the various topics of analog circuit design with you throughout the past few weeks, and I hope you found it an enriching experience. I hope you got some value out of the discussions we had, and please send me an email if you have any doubts. My email ID is please contact me if you have any questions. I shall be very happy to provide answers to your questions. Also, please let me know if you felt that some more topics needed to be covered or something which we had to cover in more detail. Of course, we have a time constraint of 20 hours for this course, and that's why I tried to squeeze as many topics I could within this time that we had. But I would definitely, if I receive some emails from you regarding some particular topic that you are interested in, we can discuss on that. Thank you.